Hello and welcome to this video here. In this video we're talking about limits of functions. So the idea is we are going to extend the notion of limits that we have introduced for sequences to functions. So this is called limits of functions. And we're going to start with an example application to illustrate the idea or the necessity of discussing function limits. Now, let's say you are a wholesaler, for example, of liquid disinfectant, and you want to offer your customers special conditions if they buy a certain amount of disinfectant. There's a minimum amount they have to buy, let's say 500 liters per order. There's a maximum amount they can buy per order, that's 2,000 liters. And if they decide to buy more than 1,000 liters, you are going to offer them a discount on the price. So the conditions are the following. A wholesaler of liquid disinfectant offers the following conditions. First, the minimum order is 500 liters. The maximum is 2,000. The price up to 1,000 liters is €3 per liter. And if a customer orders more than 1,000 liters, then the wholesaler charges a fixed amount of €2,500 for the first 1,000 liters, and then €2 for each additional liter. So up to and including 1,000 liters, the price per liter is, let's say, €3. And furthermore, for orders over 1,000 liters, the wholesaler charges €2,500 for the first 1,000 liters, plus an additional €2 for each additional liter. Now, in mathematical terms, that means we have a sales price function that is dependent on the quantity of the sales. We call this function f, and it's defined on the interval from 500 to 2,000. Both bounds included. And the codomain is R, or let's say the non-negative real numbers. And that function is defined as f of x. X is the quantity of the order. That is either 3x, so 3 euros per liter, if you order between 500 and 1,000 liters, and it's 2,500 plus 2 times, so that's the fixed amount, 2,500 for the first 1,000 liters, and then we charge 2 euros per additional liter, so we need to multiply this by x minus 1,000. That's the liters above 1,000, and each of those costs 2 euros. And we have that for x in 1,000 excluded, up to 2,000 included. So we can of course simplify this a little. This lower part here, this can be simplified to 500 plus 2x. And if you look at the graph of that function, you'll notice the following. We have 1,000, 2,000, 3,000, 4,000, and 5,000. So those are the, this is the total price of an order. 1,000 euros, 2,000 euros, 3,000 euros, 4,000 euros, 5,000 euros. So this axis here displays the total price, f of x. And here we have the order quantity. Let's say here's 500, here's 1,000, here's 1,500, 2,000, and so on. Then the minimum order is 500 at 3 euros per liter. So this corresponds to a total price of 1,500 euros. That 3 euros per liter are in effect until up to an order of 1,000 liters. So for 1,000 liters, you would pay 3,000 euros normally. So that's up here. And that point is included. So here's the first part of our price function. Then if we order more than 1,000 liters, we pay 2,500 euros on the first 1,000 liters. And then 2 more euros for each additional liter. So if we order 2,000, then we pay 2,500 plus 1,000 times 2, so that's 4,500. That means for an order of 2,000, here, that's 4,500. And that means this is how the function looks like in that part here. So you can see that there is this little jump here at 1,000. And obviously if you approach this from the left, so if you order 1,000 or less, then this is the point that you're approaching. So you could say this is the limit of the function coming from the left or from below. Whereas this here is a point that you would be approaching if you order 1,000 liters but approach from above. So if you start with a higher order and then decrease your order until you're just above 1,000 liters, this is the point that you're approaching. So this could be called the limit from the right or from below, from above. Okay, so that's why we are going to deal with limits of functions. One reason why we're going to deal with limits of functions. We want to be able to investigate situations like this, where a function has a jump like that. Of course, we're also going to deal with different situations that involve limits, but that is a prototypical situation where we need limits. And you can also see that this pricing information is not quite consistent you wouldn't order 1,000 liters. You would rather order 1,000 liters in one and then throw away 1 liter here because of this jump here. It doesn't pay to order 1,000. It doesn't pay to order anything above this line here. You would order more to be on this line instead. And we're going to repair this later with an adapted pricing function. So let's see how we can define function limits. So here's the precise definition. And what we're going to do is we're going to use the notion of sequence limits in order to define function limits. Usually for function limits, we're going to assume that we have a function defined on an interval. Of course, the real line or any open interval is also fine. So the boundaries may be infinity or minus infinity. That is totally acceptable. But what we want is we're usually going to investigate a single point. And we want the neighborhood of that point. So the points to the left, some points to the left, some points to the right. We want those to be included in the domain of the function. And that's why we usually assume an interval as the domain of the function. So let's start with an interval. We call those I. So let I be a subset of the real line. That is an interval. And we'll consider a single point. We call that x star in the interval. And f, a function defined on the interval, we can exclude the point x star here, because that is the point that we're going to consider for a function limit. So we don't need the function to be defined here. So this is a function on the interval I with the possible exclusion of x star. Of course, x star can also be part of the domain, but it doesn't have to be. So, first part of the definition. When is a function convergent as x tends to x star? So we are interested in limits of f at the point x star. We first define the function f is called convergent for x to x star. So you'd pronounce this as x tends to x star, or just x to x star. If there exists a number gamma in the reals, with the following property. And the property we want is, if we take a sequence in this interval with the exclusion of x star, and that sequence tends to x star, then we want the sequence of function values of the sequence to also converge. Let me write that down to make it more clear. So, for every sequence xn with index at n0, with elements in I with the exclusion of x star, with limit of xn equals x star. So a convergent sequence that converges to x star to the point that we're interested in. If we have such a sequence, we can define a new sequence by just taking the function values of xn. So we define a sequence f of xn. And we want this sequence to also be convergent And we want the limit of that sequence to be gamma. And most importantly, we want that to be true for every possible sequence, not just for 1 or 2 or 5, but for every possible sequence of xn's that converges to x star, no matter how it behaves otherwise. So this is the important defining property here. And we'll refer to that later, so we'll mark that as the property star. This number gamma is then, of course, called the limit of f as x approaches x star. So the number gamma is then called the limit of f as x tends to x star. Or simply for x to x star. And this limit is denoted in the usual way by saying this is the limit of f of x. And now, of course, we have to denote that this is the limit as x tends to x star, so we write that below our limit here. So this is gamma, or there is an alternative definition or alternative notation that you can also use. You often write f of x tends to gamma as x tends to x star in that way here. So this is the first part of the definition. That is not sufficient for the situation we have at hand in our example, because there are sequences. If you back here, there might be sequences if we're coming here from above, sequences like this one that tend here, where that limit would be this value. If we have sequences here, down here, that tend to 1,000, then we get this value as the limit. So obviously those two do not agree. And that's why we also want to define what we call one-sided limits, because this is the case very often in practice. And we define those in the same way by just restricting the sequences to those that lie on the left, completely on the left of x star, or completely on the right of x star. So if the sequences in this property star are restricted to those for which either xn is strictly less than x star. Let's do those first. For all n in n0, then we call this number gamma the limit from below or also limit from the left. And of course, the same notation can be made for a limit from above or limit from the right. What we need here is we need xn to be strictly greater than x star. And if that is the case, then we call gamma the limit from above. Or limit from the right. The notation is similar to the one that we have already seen. So we either have limit of f of x equals gamma, and for the limit from below, we write x tends to x star in this way to denote that it tends to x star from below. Or sometimes we also write limit f of x equals gamma. We use x to x star, and then we denote the limit from below by adding a minus superscript here to the x star. And similarly for the limit from above, in that case, we either write that arrow as a downwards arrow like this, x to x star from above, or we denote that by adding a plus superscript to the x star like this. And as I already mentioned, these limits are also called one-sided limits, in contrast to what we defined in the first point here. Okay, point 3, that's a very simple one. If a function has a limit, then we just say the limit of f for x to x star exists. And the same is true for one-sided limits, of course. So if f has a possibly one-sided limit for x to x star, we say the limit, or the one-sided limit, let me add that as well, of f for x to x star exists. Please take note that this limit has to be a finite real number. So if it's infinity or minus infinity, then we will say it does not exist. But of course, this notion can be extended to a gamma that is either plus or minus infinity. We would then say the function tends to plus or minus infinity. And of course, we can also use plus or minus infinity for x star by just taking sequences that tend to plus or minus infinity as the basis of our definition in this star property. And that's the last part of this definition. So the notion of function limits can be extended to either gamma in minus infinity plus infinity, one of these two, and or to x star in minus infinity plus infinity. And the notation is, of course, as you would expect, the limit of x to x star of f of x is then plus or minus infinity, but still we would say the limit does not exist. So let's maybe add that as a remark. And for the case of x star being plus or minus infinity, we just use that here. X tends to plus or minus infinity. That is, of course, necessarily a one-sided limit in that case, but we will not use the notation for one-sided limits here. Just out of convention, we just use f. Limit of f as x tends to plus minus infinity as usual, and that will be gamma. And that limit can, of course, exist if gamma is finite, or could not exist if gamma is infinite. So that is the precise definition of a function limit. As a quick remark, there is, of course, a relation between limits and one-sided limits. A limit for a function exists if and only if both one-sided limit exists and coincide. So the limit of f for x tending to x star, this exists if and only if both one-sided limits, so the limit of f of x as x tends to x star from below, and the limit of f of x as x tends to x star from above, both exist and coincide. And if you think back of our example here in the very beginning, this one here, you can see that both one-sided limits do exist. So this here is the limit from the left. This is the limit from the right, but they do not coincide. So in this case, the limit would not exist. Let's round this off with a quick theorem. Two quick theorems that tell you something about how to work with limits that stem directly from their equivalent limits, from their equivalent theorems for sequences. The first one is about a few rules for function limits. And of course, you can combine functions in similar ways as you can combine sequences, and the limits for functions behave in the same ways as the limits for sequences will behave. So that shouldn't be too surprising. Let's just write it down. So let's say, again, we have an interval. Let I be a subset of R. Be an interval. Let X star be some point in that interval. And let's say we have two functions, f and g, defined on this interval with the possible exception of I star. Codomain is R. So let those be functions on I without X star. And let's say both limits of f and of g as x tends to x star do exist. So if both limit f of x as x tends to x star and limit g of x as x tends to x star, if both of these exist, then the following hold. First, you can just add or subtract these two functions, and that will then lead to an existing limit that will also be the sum or the difference of the limits of the single functions. So more concisely, the limit of f of x plus or minus g of x as x tends to x star is the same as the limit of f of x as x tends to x star plus or minus the limit of g of x as x tends to x star. You can also multiply those two functions, so that's the second point here. The limit of f of x times g of x as x tends to x star, that also exists and is equal to the limit of f of x as x tends to x star multiplied with the limit of g of x as x tends to x star. And of course, if you can multiply, you can also divide those two functions, provided that g of x is not 0. So if the limit of g of x as x tends to x star is not 0, then this limit here of f of x divided by g of x, x tends to x star, also exists and is equal to the limit of f of x, x tends to x star divided by the limit of g of x as x tends to x star. And of course, all of these also apply to one-sided limits. So that's the last point of this theorem. The above statements also apply to one-sided limits. And finally, let's talk about something that is referred to as the sandwich theorem. That also exists for function limits. So that's our last theorem for this section here. Again, the setup is as usual. So we have an interval, so let I subset of R be an interval. Let X star be in I, and let F G and also H be functions defined on I with the possible exception of X star, and that map to R. So those are functions such that, let's say, the limits of f as x tends to x star and the limit of h as x tends to x star, we want those to exist. And then first we have a theorem that compares the possible limits. So if f of x is less or equal to h of x for all x in I, then also the limit of f of x is less or equal to the limit of h of x as x tends to x star. So the inequality carries forward to the limit, same as for sequences. And the second point is the actual sandwich theorem. If in addition to that, f of x is less or equal to g of x is less or equal to h of x for all x in I. And if the limits of f and g and h coincide, so if in addition the limit of f of x as x tends to x star is equal to the limit of h of x as x tends to x star, then the limit of g of x as x tends to x star exists. And its value is of course equal to the one of those two other functions. So we can say the limit of g of x as x tends to x star is equal to the limit of f of x as x tends to x star. And finally, a last note, this is also true for one-sided limits, and of course also for x to plus or minus infinity. So analogous results hold for one-sided limits and for x to plus or minus infinity. So this concludes our fairly long and little technical definition of function limits. In the following videos, we'll have a look at a few examples of how to actually compute function limits, and I'm sure I'll see you then.